1 and a polymerase 2. And I'm going to tell you that that's the case, but there's also a polymerase 4 and 5. So E. coli have 5 different polymerases. And I'll just mention here that polymerase 1 and polymerase 3 are the pols that are important for normal DNA replication. Okay, so the stuff that we're discussing here. Polymerase 2, 4, and 5 are also important for replication, but it's to repair damaged DNA. Okay, so as elongation occurs, let's say we have finished putting all the nucleotides on the strand, and you have to remember one thing, that part of DNA, part of the daughter strand, it has to be identical to the parent strand. So there's one thing here that we need to get rid of. We need to get rid of that RNA primer and fill it in with DNA. And so the protein that does that is in fact called 1. Okay? So its job is to get rid of the primer and then fill in with DNA. Okay. So, I'm going to take you back to these pol rules again, mainly this 5' to 3' rule. So just to kind of recap here, this existing strand rule is solved by primates. And the single-stranded DNA rule is solved by a myriad of different proteins, but one being the single-stranded binding protein, and then all the initiating protein that started separating the strand. Okay, so so now we're going to talk about the leading and the lagging strands. Okay, so imagine you have your DNA. And your replication fork is here. And the direction that the DNA is unwinding is that way. And I want you to remember that this is actually only half of the bubble. And so imagine that this is also, there's a mirror here, and this exact diagram is also drawn here, and you have another fork going in that direction. And this replication, just always keep that in mind with bacterial replication, that it goes in a big, huge circle in opposite directions. And if I haven't mentioned it yet, that's called bidirectionality. Okay, so you have your fork. This is your 5', this is your 3', 3', 5'. And those dots means that it continues the other way. Okay, so we can replicate in 5' to 3'. So here we go. Here's 5', and you start adding the nucleotides one by one in this direction. And that's no problem, because as this keeps unwinding, because we're still going in the 5' to 3 direction, 5' to 3' direction in the new strand, you can basically just keep adding your nucleotides without a problem. So on the other strand, so this is called the leading. This is called the leading strand. Okay? That's not a problem. But as you're separating your DNA, so let's start here. This little box here just represents the RNA primer, okay, before it was removed. So this is your 5' end of your new strand, and you're adding your nucleotides in one by one, 5', and then to 3'. Okay, so now let's take some time and let the DNA helix unwind a little bit. So what we have is our this initial strand here was made there. So you have 5' to 3'. And your initial strand on the leading strand initiated here at the very end and has no problem adding on nucleotides.
Wait, sorry, I'm just a little confused. On the top diagram, it says if we only add from 5' to 3', then why are we coming from a 3' direction?
So it's not on the parental. The 5' to 3' rule is not. It's not in relation to the parental strand. It's in relation to the new strand that you're making.
Oh, okay.
Is everyone clear with that? So that was something, when I took genetics, it was really a hard concept for me to grasp because it seems counterintuitive. So the reason why we're starting it here on the 3' end of the parent strand is because polymerase adds 5' to 3'. So your new strand, so we remember that DNA is always 5' to 3', and then on the bottom it's opposite. So if this was your parent strand, the rule applies to the new strand. So this would be the new strand. So you can start there, and now you are adding 5' to 3' on the new strand. Okay, so let's draw that a little bit. So on this lagging strand, this is the 5' most area that you can get to because you're hitting that replication point. So you're putting your RNA primer and you're adding your nucleotides on your new strand, 5' to 3'. Okay, so this is now down here. And so you can keep adding these nucleotides, no problem, to get all the way to the end. But now we have to start again because this is unwinding that direction. So you can't add nucleotides this way. So what the machinery actually has to do is primase actually has to come in again and add a new RNA primer where the replication fork is. And so then polymerase comes in and adds nucleotides 5' to 3'.
Isn't leading and lagging relative to your orientation as well? Then? No.
Yeah, definitely. It's relative to your orientation and it's relative to the replication fork. So leading strand is going to be making a new strand towards the replication fork, or that's the orientation of the replication fork. And then the lagging strand is going to make the new nucleotide sequence going away from the fork. So remember that in this case, so you have your order replication here. You're going to have both a leading strand and you're actually going to have a lagging strand as well. So here. Okay. All right, so what you're going to have is your leading strand will move in this direction, but so this bubble here was once a double-stranded DNA. And so all that machinery made it this big bubble. So for the sake of clarity, I'm going to now put an ORI down there because both strands are going to have an ORI. So you have your ORI. So from this strand, the orientation of replication, you're going to have your leading strand move in a 5' to 3' position. But then from this ORI, you're going to have lagging strands, but they're still going to go in this direction because this is the replication fork, it's going that way, and this is another replication fork going this way. And so from here you have a leading strand and a lagging strand going that way. And then you have, from this ORA, so from the other strand, you'll have your leading strand going this way in the direction of that replication fork, and then your lagging strand go this way. So if you see something here, everything is going 5' to 3'.
Is that bottom one also going that way too? Because you have a draw going so you have column.
So 5' to 3', 3' to 5'. So you remember before we started, the origin of can you guys probably not see that?
You can push the laptop down or the screen down. It goes into that divot. Push. Yeah. You can lift the thing up and then close it down on it. There you go.
It's fine, it's a Windows.
Okay. So before the replication bubble began, you had one ORI. Okay? And then the replication bubble formed. So now you have something like this, where the two strands, so you have your ORI here. And if this was originally 5' to 3', so if you start here, this is kind of what we're emulating here. So this is this spot right here. So from that origin of replication, you have your, so when you're adding your new strand, you're going to start 5' to 3', and you're going to add the nucleotides this way, all the way to the end of the string. That's going to be your leading strand because it's not getting backed up by needing to hop back to the replication. But what happens, now let's look at this bottom origin of replication from the other parental strand. So this one, you're going to need to go and add fragments that way.
Wait.
Question?
Yeah, I'm just getting confused because on the previous drawing you have a drawing going the other way. I think that's where I'm
Okay.
lost.
Okay. Okay. So, all right. So from this end, you're going to have your leading strand. So the reason why maybe I'm confusing you guys is this is only one half of what's going on. So this strand right here and this strand right here, yeah, you're right. My bad. Okay, so sorry you guys. Let's try this again.
It just makes us feel a little bit better. But
What?
it's confusing to everybody.
It is confusing and it's
Basically, what's going on is from point of origin, you got two of each strand going in opposite directions.
yeah. Yeah, and that's what I'm trying to portray to you guys, but I'm obviously not doing a great job. Thank
So
you.
potentially it would be the piece, the primer or the primase, the part where it's starting that's closest to the 5' end is going to be the leading strand.
Closest to the.
From 5.
It's going from 5 to 3, but the
Right, but
thing
it's
closest.
going towards the fork, so this is where it's splitting. So it's as if there's no bumps in the road. So it just continually
Oh,
goes.
yeah, yeah. Okay.
And then the other side, because it's still you're going to have bumps, but it just has to keep coming back and catching up to where, filling out the gaps where it's still opening up to. And there's,
Yes. So, thank you. So, let me clarify some things here. The